Okay, just to kind of finish up the next page, there's another buzzword to draw your attention to here. Okay. So sorry, just to take the last page of the question here. So part 6, there's your buzzword there, rates. So find the rate. Remember, so rate means derivative. That's a calculus question. Okay? So find the rates at which the population of the two plants are changing when t is equal to 6 and explain these results in the context of the question. Okay, so rate means derivative. So this is a differential calculus question. Okay, so in the case of this one here, that if you so Michael was asking there on the previous one, can you not let the population function equals 1 and solve to find a value? So can we maybe try and solve it? But remember, if you were trying to solve this to find when the time is 0, all right? So I say, look, there's my formula. So 17740 times e, or this one, whichever way you want to phrase it, okay, times e to the power of minus 0.09t is equal to 0, because it says in the question how long it takes to drop to 0. Okay, you can't put it equal to 1 because that's not what he asked you. Right, so if you put it equal to 1, you may be able to find a very, very small time value, all right? Or sorry, a very big time value, all right? But that's not what he asked you, so he'll only give you partial credit for that because it's not what the question asked, right? So if you put it equal to 0, that when you divide across by this, divide by that, 0 divided by this number still gives you 0. So you get e to the power of minus 0.09t is equal to 0. So just dividing across by this number here gives you a 0, right? That's fine. Now, how do we get rid of e to the power of? I'll go with natural log on both sides. Right? So if in an exam I didn't spot that this was a theoretical question and I tried to solve the equation, right? I get natural log of 0 like that. So here these guys cancel and I get minus 0.09t, and when you put that into your calculator, you get a math error. Right? Because the log of 0 doesn't exist. Right? So if you get that far, now that's your partial credit, that for sure. Because you haven't made a mathematical error. All you haven't done is you haven't explained why we got a math error here. The reason is that the log of 0 doesn't exist. Now that might in exam trigger a memory. Oh, hang on, yeah. Isn't that the one that takes an infinite amount of time to get there? So if you put this down here and use that as your justification, that's full marks. You're okay. But I wouldn't put it equal to 1 because, as I said, 1 is not what was in the question. So you only get partial for that anyway, because you'd say, look, that's not what I asked you. I didn't ask you how long it takes the population to get to 1. I see what you're saying, that the population, it's as small as the population can be without being 0. But it's not what the question asked you. So if you put it equal to 0 and solve, you get a math error here because the log of 0 doesn't exist. And that might trigger a memory. Oh, hang on, I remember why now. Okay? Right. So the last part then, part 6. We're asked to find the derivative. Rate means derivative. And now we've got to do the differentiation. So if we look at A first of all. So again, I'm going to write the population of A this way. I'm going to multiply the 0.82 by the 10 to the power of 3, because that's the number in front. Let me just tidy all that up. Times e to the power of 0.13t. All right? So I want to find the derivative, which I'm just going to call this. So when you're writing the name of a derivative, whatever letters on the left-hand side goes above the line, and whatever it is on the right-hand side goes below. So it's dpa, it's the change in the population of plant A over the change in time. Okay? He won't penalise if you call it something incorrect. If you just call it dp, dt or something, he won't penalise that. But just try and keep your terminology clear. It'll be helpful when we get to calculus later on this morning. Okay? So dpa dt looks like that. So to do the differentiation, remember when we were doing integration, we did number, function, bracket. Right? So number... the number right in front here. Function. Okay, the e to the power of. And remember, when you're dealing with an exponential function, the power is the bracket. Okay, number, function, bracket. So when you're integrating, the number in front stays put. Page 26 tells you what the function turns into, and then divide by the derivative of the bracket. That's when I'm integrating like we did in the previous part of the question. When I'm differentiating, the number stays put. So the 820 stays where it is. Okay. Now function, I go to page 25 this time. So page 25 will show me what happens when I differentiate. Right? So remember the previous page here. There it is. Page 25. there's my derivatives. And there's the one I'm looking for. Right, there it is there. That again, e to the power of stays the same. Right? And the very same thing that Vicky pointed out earlier on. Okay, I could use the rule just below it in the table. Because in my function here, e is multiplied by a power. All right, that's perfectly correct. All right, but I'm just going to use this number function bracket thing. So the function again stays the same, e to the power of 0.13t. And this time I multiply by the derivative of the bracket. And if I differentiate 0.13t, I get 0.13. Because remember, when you differentiate something like that, you're using the chain rule. And that's what they really do with the chain. So the function bracket bit is the chain rule. Okay, where I do the outside function first, the e to the power, and then I do the power here. I don't need to pull it apart in my head that way. This number function bracket thing will work every time. So when you're differentiating, the number stays put. Page 25 will tell you what the function turns into, and you multiply by the derivative of the bracket. When you're integrating, the number stays put. Page 26 will tell you what the function turns into, and you divide by the derivative of the bracket. And that will work for all the other functions we're going to have a look at in the next couple of questions as well. Okay, I'm hoping that makes a bit of sense. Right. So, if I do that then, so that's my answer. I would just tie this up by multiplying these two together. Okay, so I multiply those two together. I don't have to because I'm subbing in a value, but just to tidy that up, I could multiply those two numbers together. I'm not going to bother, but if you multiply those together there, but remember what I need to do now is put in the value, which is 6. So when t is equal to 6, dpa dt is just 820 times e to the power of 0.13 by 6 times 0.13. I can just pop that into my calculator. And for the same reason we talked about earlier on, I would put this to the nearest whole number. Again, there probably won't be a penalty if you don't. Okay, it'll be 1 mark maximum if you did. But if I put that in, it's about 233. Right? So when I put that in, I'd round that to the nearest whole number. And what are the units? Think about that for a second. So what the units are here. Right? So remember, the units are these units per those units. So what's that measured in? Plants. And that's measured in months. So if you like, that's plants per month. Although, because remember, plants are not a unit of measurement, it would be okay to leave that and just say 233 per month. Now, we'll explain what that means in a second. So you could leave out the word plants because it's not a standard unit of measurement, okay? But the units for a derivative, it's these units per those units. So what's that measured in? What's that measured in? It's one per the other, okay? So it's 233 plants per month. Now, we'll write the expansion in a second, but what does that mean? Because that's a positive number, it means the population is increasing by 233 plants per month. That's how fast the population is changing at the 6-month mark for plant A. Okay? So, let's do the same then for plant B. Find the derivative there as well. So, for plant B, again, I'll multiply the two numbers together, so I get 17740 times e to the power of minus 0.09t. So I just multiply the 17.74 by the 10 to the power of 3, just keep my whole number together like that. So again, to find the derivative there, dpb dt, all right, number function bracket. So the number, the 17740 stays put. Okay, that doesn't go anywhere. What happens e to the power of? Well, that stays the same. Page 25 tells me that. So it's e to the power of minus 0.09t. And then bracket, remember I multiply by the derivative of the bracket. And if I differentiate minus 0.09t, I get minus 0.09. Like that. And again, I'll just sub in my value. So I put in t equal to 6, I get 17,740 times e to the power of minus 0.09 by 6 times minus 0.09. All right? And when I do that, that comes out at, again, to the nearest whole number, it's like minus 930. And it's the same thing, plants per month, or minus 930 per month. So again, because that's negative, okay, because that's negative, that means the population is decreasing, which makes sense, isn't it? Because in the graph we had earlier on, that we just sketched, remember the plant A does that, it's going up, so that's why that's positive, okay, that the population of plant A is increasing always. The population is always going up. And plant B looks like this, it's going down that way, all right? And plant B is going down because of the minus sign here. So it's decreasing by 930 plants per month. Okay, so we'll comment on that now. So Alan's asking there, how come you don't use the product rule to solve? So why don't I use the product rule here? So remember, the product rule is only used when I'm multiplying together two things which are both functions. So what I'm multiplying together here is a function by a number. Now, if you use the product rule there, you'd be saying, look, u is 820, right? And v is e to the power of minus 0.13t. Right? So you can see the two things here, one of them is just a number. That's why I don't need the product rule. So if the two things you're multiplying, one of them is just a number, I don't need that. Now, if you did use the product rule here, what happens when I differentiate 820? It's a constant, I get 0. Right? And what do I get if I differentiate this here? Well, when you use your chain rule there, don't you get e to the power of 0.13t multiplied by 0.13? Remember, you just multiply by the derivative here. So see, when you multiply these two together, they'll disappear because 0 by anything is 0. I just get 820 times this, which is what I got anyway. So if you did use the product rule, it'll get you the right answer, but you don't need to use the product rule when it's two things multiplied together and one of those things is just a number. That's why. Because when you differentiate the number, this part of the product rule will disappear. Does that answer your question? That okay? Right, so that's the thing. So just to explain what these two mean here, okay, what those two mean, all he wants you to comment on when you're asked to explain what a rate means is, explain what the number you subbed in means, and talk about the sign. They're the two things to comment on, right? Because the actual number itself here with its units explained itself. So 233 plants per month explained itself. But what I do need to comment on is the sign and the t equal to 6, right? So what does it mean when t equals 6? It means after 6 months. Okay, so I do need to mention that. So when you're explaining what a rate means, comment on what the value you subbed in means. So after 6 months, when t is equal to 6, and that means after 6 months, okay, A is increasing. Okay, so I've got to mention that because for A, the derivative is positive. It's increasing by 233 plants per month, or by 233 per month, okay? And B is decreasing by 930 per month. Okay, that's what the minus sign means. So if you're talking about a rate, mention those two things, what the number you subbed in means, and what the sign of your answer means. Positive means increasing, negative means decreasing. Yeah, Peter, I'm very efficient. But don't worry if you're not as efficient as me, Peter. Nobody is. Okay, don't aim too high, all right? Mid table's perfectly fine, okay? So 233 going up by 233 or going down by 930. Now, the last part of that question, I'm deliberately kind of milking this one a little bit because there's a lot in this. It's a great opportunity to talk a bit about differential calculus. When we meet the calculus in the other questions, we'll be able to blitz through it a bit quicker. So there's no harm in pulling this one apart. There's a lot of kind of good revision in this one, right? So the last part of the question, part 7, when do the models predict the populations of the two plants would be equal? Now, if you remember back in 2017, so 2017, paper 1, question 7, right? That's the first time he asked this question. It was the question about the two cities, Sapphire City and Avalon, which was the same kind of idea. The population of one city was going up and the other was going down. And he asked this question, okay, after how long are the two populations equal? And he's asked it twice now since then as well. So this question where you're trying to find where the two populations are equal has been asked a couple of times, right? And it's actually quite a simple idea. There's just one kind of step that he's really testing you understand, okay? So we want to find what the populations are equal, so just put the two formulas equal. So even if I had them in their original formula, that 0.82 times e to the power of 0.13t by 10 to the power of 3 equals 17.74 times e to the power of minus 0.09t by 10 to the power of 3. So you can see straight away, if I had them in that formula, I could just cancel the 10 to the power of 3's on both sides anyway. Okay, it doesn't matter if I'd used them in this form here, it doesn't make any difference. But if I left them in the original form, the thousands will cancel anyway. So what you want to do now is get the two numbers on one side and the two exponents on the other. But you can't do that by moving stuff, because they're multiplied together. I've got to do it by dividing. So what I would normally do here is divide both sides by the smaller number. It doesn't matter, you can divide by either number. Couldn't make any less difference. But if you divide by the smaller number, it just makes sense. So I'm going to divide both sides by the small number, the 0.82. So I divide that side by 0.82 and divide that side by 0.82. So on the left-hand side, they'll cancel. And I get e to the power of 0.13t is equal to 17.74, like that, over 0.82. Right? So the two numbers are together on one side, like that. Okay? And then, so you can see with the two numbers over here, all I want to do now is divide across by this guy to get the two exponents on the left. So by dividing, put the two numbers on one side, the two exponents on the other side. Sorry, Keane, this is on page, where are we now? Page 8. Okay, so page 8 there, Keane. So here, if I divide across by this then, I get e to the power of 0.13t divided by e to the power of minus 0.09t is equal to 17.74 over 0.82. And you've got your partial credits for getting that far. Okay, you probably got 5 out of 10 for hitting that point there, for getting the two exponents on one side and the two numbers on the other, right? And all the question is testing now is, do you know how to tidy up the left-hand side here? That's all the question is about. And to do that, I just use one of my rules of indices, again from my formula booklet, okay? So my formula booklet, here, page 21. There it is. There's the rule I'm looking for. Okay, this one. See it? If you've got a number to one power divided by the same number to a different power, you just subtract the powers. So a to the power of p divided by a to the power of q is just a to the power of p minus q. That's all this question is testing. Okay? So, do I get that? So all I've got to do here, because it's the same number to two different powers, just subtract the powers. So it's going to be what? 0.13t minus 0.09t. Just this power, take away this power. Remember, minus by minus is plus. So that's going to be what? 0.22t. So I'm going to get e to the power of 0.22t is equal to that number there. And now, gentlemen, start your engines. Just another exponential equation to solve. Just use logs to remove this and then divide by 0.22. So the whole question is just testing that. Can I get from here to here? That's all the question is. There's nothing else beyond that that you haven't looked at already. Okay? So, if I just finish it out then, I'll take the natural log of both sides. So the natural log of e to the power of 0.22t is equal to the natural log of 17.74 over 0.82. Right, over here they'll cancel and give you 0.22t is equal to, if I pop that into my calculator, I get it's about 3.074. And then divide across by the 0.22, I get that t is about 14. Again, you don't have to round to a whole number, but it won't be penalised if you do. It's close enough. And again, remember, t is in months. It's a 1 mark penalty if I don't include my units. So after about 14 months, the population of the two plants will be equal. Now, that's a really good question to work our way through, because everything we need for exponential functions is in there. And it's given me a chance to talk to you a little bit about differential calculus and integration. All right? So everything he's ever asked kind of on exponential functions is tied up in that one. Anybody any questions on that one? If you have, pop them in the chat. Otherwise, we'll kind of push on with the next question. So with the next couple of questions, we kind of get through a little bit more quickly, because I've kind of talked through a lot of the theory and words to watch out for already in that first question. We okay? Right, we'll crack on, then we'll have a look at the next question, then we'll have a look at question 2. Let me just bring that up here. Right. So, question 2 then is on page 9. It reads like this. Now, this is a logarithmic function. I think of all the ones here, this is maybe a little bit more likely. Okay, a logarithmic one. There hasn't been one of these now since 2022. So 2022, question 10, he asked one of these. So it says, when tickets for a music festival go on sale, the percentage of tickets sold, P. Okay, so P is a percentage. That's the units there. So P is percentage. after t hours, so t is in hours. So they're my units. P is percentage and T is hours, can be modeled by that formula there, and we're asked to complete the table below and then draw the graph. Okay, so that's quite a simple question, right? So that's just, so what you're going to do there is use the table function of your calculator, right, to fill out those values. You can drop the numbers individually into the formula, but it's quicker if you know how to use the table function of your calculator, okay? There's a calculator guide on the platform for you, where you can, I talk you through on the newer Casio how to use the table function, all right? So if you use the table function there, you can fill out the table very quickly and plot the graph. Now that's money for old rope. If you get a long question with a graph in there, the graph might be worth only 10 marks. It might be 5 for the table and 5 for the graph, but usually it's more than that. In the 2014 question, it was 10 for the table, 10 for the graph. That's 20 marks out of 50 for just drawing a graph. So it's worth kind of having a look at that and making sure I can do it. All right. So I won't kind of waste our time, spend a lot of our time doing it here. But I'll just kind of pop the values in really quickly here. So the values there end up being 0 because it does say to round them all to the nearest whole number. Okay. So that's 0 in the first one. Okay. Right. So that's 0 there. And the next one is, it's 64, 79, 88, 95, and 100. Okay, when you're on the nearest whole number. So you can see that's 0 down there, okay, at that point. 24, we're up to 64, okay, which is there. 48, you're up to 79, which is there. 72, you're up to 88, which is there. 96, you're up to 95, which is there, and you're up to 100, and then just join them together. No, stay put. That's not bad freehand now on a screen like that. Okay, that's better than a lot of you guys will manage with the page flat in front of you. All right, so that's the graph. So it's a typical logarithmic increase like that. Now that's not terribly difficult, but just a matter of kind of bashing it out that way. So yes, you can, Luke said, can you bring more than one calculator? Absolutely, you can bring more than one, as long as they're both legal. Remember, there's a list of forbidden, banned calculators on the SEC website. They're programmable ones that will solve equations, stuff like that. So you can bring more than one with you. What a lot of people do is they'll bring even a backup copy of their own one in case the battery goes. Okay, so you can bring 2 different calculators with you, 2 different models if you want to, that's perfectly fine. Just if you are bringing calculators that are not, if you're not the standard Sharp or Casio, just check the website. Okay, make sure it's not a banned calculator, because as a rule they don't check. Okay, but if your exam is being supervised by a maths teacher who notices a calculator that's banned, it can be taken from you because they're programmable. All right, if you're just using one of the standard calculators, you can bring a second one with you. All right, I know a lot of people like the older Casio. The newer Casio is a little bit trickier to work with. So kind of saying, look, that some calculators, so I like doing some calculations on the Sharp, some on the Casio. I'm good with both. Yes, you can bring 2 with you. All right, that's perfectly fine. All right, but if you draw your graph, the graph looks something like that. And then the questions based on that then. So part 2 of the question on the next page. It says, how long does it take? There's an extra line in the question there that shouldn't be there. See where it says, give your answer correct to 3 significant figures. That's doubling up. That shouldn't be there. There's an additional line there in both part 2 and 3. That last line there, give your answer correct to 3 significant figures. That shouldn't be there for either part 2 or 3. And the rounding is given the previous line. So how long does it take? So my formula looks like this. That P is equal to 22.8 times natural log 1 plus 0.65t. All right, like that. That's my formula, logarithmic one, 65t. And it says, how long does it take to sell half the tickets? Well, remember, P is the percentage of tickets sold. That's we marked out when we read the question to begin with, that P is the percentage of tickets sold. So when half tickets are sold, P is 50. So 50%. So if I put P equal to 50 at that, there's my partial credit straight away for putting that value in correctly. Right? So P is 50 because half the tickets is 50%. We marked in the question that the units for P were percentages, and so half is 50. Right? So if I divide across by this number here then, I get 50 over 22.8 is equal to the natural log of 1 plus 0.65t. Now, the question is, how do I get rid of natural log? right? Well, natural log, remember, as we pointed out already, if you've got this equation here, 3 to the power of x equals 81. To remove 3 to the power of, I'll use log to the base 3. Powers and logs are opposites. So if I go with log to the base 3 on the left-hand side like that, because these base numbers match, they are opposites. They're like a square and square root. They'll cancel and leave the x behind. So whatever I do on the left, I've got to do on the right. And if I put this into my calculator, I get the correct answer 4. So that's how I solve an exponential equation. What about an equation that looks like that? Log to the base 3 of x equals 5. Right? So in this case here, remember that if log to the base 3 and 3 to the power of are opposites, I can use one to get rid of the other. So if I can use log to the base 3 to get rid of 3 to the power of, I can use 3 to the power of to get rid of log to the base 3. So if I go with 3 to the power of the left-hand side, like that, so 3 to the power of the left-hand side, that's going to equal 3 to the power of the right-hand side. So go with 3 to the power of both sides. So again, because these two are opposites here, these base numbers match, they'll cancel, and I just pop into my calculator 3 to the power of 5, which is 243, which is the right answer. Now, I know a lot of you guys, when you're dealing with log equations, are shown a shortcut, which is perfectly fine. I'm a big fan of it, where you kind of say, look, it's that number there, okay, to the power of that number there, okay, equals that number there. So you can just say this to the power of this equals this. That'll give you 3 to the power of 5 equals x, which will give you the same correct answer. That's perfectly fine. So if you were shown that shortcut, that's perfectly fine, full marks for leaving cert, there's no problem with that. But this is where it comes from. What you're actually doing is taking 3 to the power of both sides, because 3 to the power of and log to the base 3 are opposites. So 10 to the power of and log to the base 10 are opposites. Whichever one your equation contains, you can use the other one to remove it. Right? So remember, natural log is log to the base e. So what's the opposite of log to the base e? E to the power of. So to remove natural log, I'll go with e to the power of. To remove e to the power of, I'll go with natural log. So e to the power of the left-hand side, like that, is equal to e to the power of the right-hand side. Now, again, you don't have to write this line down here, but that's how I'm removing it. So I get rid of natural log by using e to the power of. I'll get rid of e to the power of by using natural log. Okay? So you can see on the right-hand side, they cancel as opposites. So I just get the 1 plus 0.65t left on the right-hand side. And if you put that into your calculator, e to the power of 50 over 22.8, that gave me about 8.926. Doesn't matter how many decimal places you take there, it's perfectly fine. And now it's easy enough to find t. As I subtract 1 from both sides, we get 7.926 is 0.65t, and then divide by the 0.65, and I get that t is about 12.25, right? 12.25 is equal to t. Now, see what it says there? Give your answer in hours and minutes, correct the nearest minute. So remember, we marked in the original question that t is in hours, right? So that's 12.25 hours. So I've got to turn that 0.25 hours into minutes, okay? So 0.25 by 60, remember, is 15 minutes. So it's 12 hours, 15 minutes. You have to give it in hours and minutes, correct the nearest minute. So 12 hours, 15 minutes. If you gave it in just minutes, you'll lose a mark. Okay, so if you just multiply that by that whole thing there by 60, you lose a mark. It said hours and minutes, correct the nearest minute. So just turn the decimal part into minutes by multiplying it by 60, and it's 12 hours, 15 minutes. Is that okay? Now, the last part of that question then, part 3, is to find the rate. So again, the word rate, I'll underline that and write in derivative like we did in the previous question. Okay, because on a good day with a kind of wind at your back, you may get the low partial just for that. Depending on how bad the answer to the question is, that just is showing you understand that rate means derivative. Very often that's enough to grab those 3 marks at the bottom. Okay, but rate means derivative. I've got to differentiate this. There's no average calculation here because integrating natural log functions is not on the Leaving Cert course. So the only ones I have to be able to integrate are e to the x, sine and cosine. That's it. Okay, so I don't need the others here. So natural log is not on the course, so that's why he won't ask you to find the average value here. That would be an integration question. That's not on the course. He can only ask you rates. Okay, so rate means derivative. So there's my function. P is equal to 22.8 times natural log 1 plus 0.65t. So again, the same little mantra we did use previously. Number, function, bracket. Number, okay, function, natural log, and bracket. So remember, if I was integrating, it should be leave the number where it is, let page 26 tell me what the function turns into, and then divide by the derivative of the bracket. That's integrating, but that's not in the course for natural log. Okay? When I'm differentiating, I leave the number where it is, page 25 will tell me what the function turns into, and I multiply by the derivative of the bracket. Right? So in this case here, to find my derivative, dp dt, leave the 22.8 where it is, number stays put, and what does natural log turn into? Well, again, we'll take a quick trip to page 25 of our formula booklet. So page 25, remember, is where the derivatives are, and there it is there. You can see natural log here, becomes 1 over. So because it's a derivative we're finding here, it's on page 25, and it tells you, that natural log turns into 1 over. Okay, that's all we need there. So the natural log of this becomes 1 over that. That's the function done, and then bracket multiplied by the derivative of the bracket. It's the chain rule you're using, right? So if I differentiate the number 1, it disappears, and 0.65t just becomes the number 0.65. There we go, like that. So that's what your derivative looks like. And if you wanted to, you could tidy these two numbers, multiply these two numbers together here to put it above the line. You don't have to because you're subbing in a value. But if I did multiply those two numbers together there, that gives me what? 14.82 over 1 plus 0.65t. That's my derivative. And then I've got a value to sub in. It says after 17 hours, I should put t equal to 17. So when t is 17, dp dt is 14.82 over 1 plus 0.65 times 17. And that comes out, it says to 2 decimal places, that's about 1.23. Now, units, it's those units per those units. What's that measured in? Percent. What's that measured in? Hours. So it's percent per hour. And because it's positive, remember what that means is the percentage of tickets sold is increasing by 1.23% per hour at that time point, after 17 hours. Right? That's what the value is giving me there. Positive means it's increasing, and that makes sense because our graph is always going up. Okay? So that's the logarithmic question. And I said, I wouldn't be surprised to see a log function like that on the paper this year. It's kind of the only one now he hasn't asked the last couple of years. So it's kind of overdue. It could be any of the 4, but I wouldn't rule that one out at all. So we'll just take a quick breather there, just for a couple of minutes, and give you a chance if you wanted to get some water, go to the bathroom if you need to. Give me a chance to grab a drink. All right.